See, today's second part mostly will be dealing with datums and maximum material condition. Okay, last time we already dealt with fundamentals and what is the difference between coordinate tolerancing and geometry tolerancing, and these are all the things we have dealt last time. I don't want to take much time on this, but today we'll be dealing with datums and also maximum material condition and virtual condition and resultant condition. And probably next session we'll be dealing with orientation, orientation like angularity, perpendicularity, parallelism. These are all the things we'll be dealing. And the last session probably will be dealing with roundness, coplanarity, cylindricity, and concentricity, run out. These are all the things we'll be dealing. So today's mostly will be confining with
20 seconds
okay. So see, somebody just about some time back, somebody is asking about symbol on drawing. This before going to this, I just want to share the difference between our old drawing practice and today's drawing practice as for ASME. As for ASME, there are some new symbols have been added, whereas our old timers we always go as per IS 616, and then that tolerance symbol, there is a little bit of difference between these two. And because we are getting the drawings today as for ASME, it is better to in these two as far as drawing symbols is concerned. So these are all common. See, here you see that whenever we make any drawing, this is the component drawing dimension, the line connected to the component, and this is the dimensioning line. He says there should be minimum 10 mm gap between this dimension and the component. This is given in standard. This is very important. I have been seeing many drawings of differences there. I just want to share that, and then I'll go to actual subject. So these are all same as our 696. See, this is one thing what they have added. When you make a drawing, there should be a difference between the dimensional lines and the component line. For that purpose, they said very visible gap is to be maintained. Today, I am seeing most of the students who make these AutoCAD drawings, there will not be any gap, and this will not distinguish between this line and this line. Both are combined. This is to be maintained very clearly. That is what ASME says. And also the dimension also, it should not be on this line. There should be minimum 10 mm gap. And one dimensional line to other dimensional line is 6 minimum gap. So this will give clarity on the drawing, and shop floor man, you will easily understand this. That is what I want to just share this. And these are all staggered dimensions. And this is one more thing here. See, you have to dimension this feature and also you have to dimension this feature. So arrows are coming, and we have to provide a break in this dimensioning lines. The extension lines, unless we provide the breaks, they will be crossing each other, and a lot of confusion is there. This is as per 1.7.2.1 of ASME 2004. So this is also to be, I just want to, my younger generation, I just want to make them clear about this. These are all the same. Here you see, this is true radius. This is not there in our 696. Though we are now, we are all following only ISO standards. This true radius is not actual radius. This radius is on this. So they have just only shown this true R20 only to show that there is a radius on this surface. That is what is true radius symbol. And this is spherical radius, and this chord length and arc length and angle. And I will just I'm going a bit faster. If anybody wants to know, and come here. Here you see, this is the diameter 8. What we write in our drawings, diameter 8 into 16 mm deep. But here they have given diameter 8 with a arrow 16. That means the depth of the drill is 16 mm. This is as per ASME. Okay. So that arrow symbol is the depth of that particular hole. Here you see he has given 2x. 2x means 2 times r. What we used to write in our drawings, two numbers, two holes of so and so, or five holes of so and so. Now the holes and other things are not there. 2x means number of. And here is one more thing. There is a hole of diameter 4, and that hole depth is 13 mm. Then subsequently there is a counter bore of dia 6, the depth is 10 mm. And again there is a counter bore of dia 10, and the depth is 3. This is the symbol. This is the symbol, and this is the meaning of this. So this kind of things are to be conversant. Otherwise, you'll get confused. Whereas in our olden drawings, what you write, dia 4, CBR2, dia 6, 10D. That is what you used to write. English you used to write. Now no more writing English. Only symbols are to be given. And like this is countersink. Earlier we used to write CSK, but now he has given a countersink symbol and no dia 10 by 90 degrees. And we also know that counter boring. These are counter drilling. Counter boring and counter drilling. This is a symbol for counter drilling. Counter boring, there will not be any chamfer here. The counter drilling, the drill bit angle will come here. That is 120 degrees or 118 degrees. And these are all and here you see this. Whenever a key dimension is dimension is given, people sometimes they give from here to here. This imaginary point, we cannot measure this dimension because we can measure only dimension from this point. So the dimension always, it is better to give from the bottom so that we can easily measure this. They are all staggered dimensions because to avoid dimensions here, they have put on a X, Y, Z format, and then they have given the dimensions somewhere else. These all are available in IS, that ASME Y14.5M. Now today's release is 2018. Okay. Now this is the taper. This taper is in the whole length. The taper is 0.15 plus or minus 15 microns is to 1. For every 1 unit of this, the taper of 0.15 meaning of that. This I want to tell only for this. Somebody has telephoned me and asking about this. Only to convey this meaning of this, I have just taken this. Otherwise, this is not there in our original syllabus. See, here we give a radius of R2.4 plus or minus 0.3. So when you take plus, it is 2.7. When you take minus, it's 2.1. Isn't it? R2.4 plus 0.3 is 2.7. The maximum radius allowed is 2.7 and the minimum radius allowed is 2.1. That means the maximum radius is 2.7 and the minimum radius is 2.7, and the job and the component can lie anywhere in between these two tolerances, and the shape can be anywhere. It can be crisscross, it can be like this, but it should, the entire surface has to be contained between these two limits. That is what we generally use in our drawings. But see, there is one more now. This is as per IS 2, that ASME class number 2.15.2. There is one specification given as control radius. This control radius means, say, maximum and minimum are controlled, but only thing is the reversals are not allowed here. The path contour, here it is there, the reversals are not allowed. If you go to earlier one, the reversals are allowed here. See, the contour can go up and down like this, or it can be straight line or any shape it can take. But once it comes to control radius, you are not allowed. Always these lines are to be tangential. These lines are to be tangential, whatever is the radius in between. It can be 2.1, 2.2, 2.4, 2.5, anywhere. But the two, always it should be, these lines should be always tangential. That description is given here. The control radius means that the limits of the radius tolerance zone must be tangent to the adjacent surfaces, and there cannot be any reversals in the contour. This is the meaning of this. Only to just convey this, I have taken this slide. I will close this and now I will go to actual topic now. Is it okay? Already, last time fundamentals I already covered. I don't want to take waste time on this. They're all fundamentals. I'll go to slides. I'm not taking much time on this because I already explained and now we'll go to types of geometry. See, in a shop floor, we always deal with three types of geometries. We get the component, in a 3D model or a hard copy, orthogonal projection hard copy, or directly we'll get a component by reverse engineering. Probably we'll be doing that measurement and again we'll be making that component. So these what type of geometries we'll deal in our manufacturing shop? Let us discuss. See, there is one geometry called perfect geometry. That is perfect, mathematically precise, as modeled, as designed, as intended geometry of the CAD systems and computer systems. Suppose in a CAD, what happens is you make a 10 mm shaft and 10 mm hole, ask it to assemble, it will assemble because there is no tolerance on this 3D model. It is exact. The 10 mm hole is exact and 10 mm shaft is exact. If you just assemble these two things in 3D model, it will assemble. But in the shop floor, it will never assemble. Suppose, no, the only God can make this kind of, perfect geometry. This is the embodiment of the part geometry in its perfect form. That's what we want, in fact. That's what we want. We always want perfect. But it is impossible to get perfect. So this is as produced geometry. This as produced, see, once you get the model or drawing, we have to manufacture the component. That is as produced geometry. This is imperfect geometry, as produced geometry of the actual part. This is always what, because it's not possible to manufacture to 0, 0, 0, 0. There is always tolerance. There are always some variations in the form. There is always variations in the position. All the things are, inbuilt into the as produced geometry. That is why it is an imperfect. How much it is imperfect? It all depends on how accurately we can measure. See, perfection and accuracy is depending on the measuring instruments. Suppose if you are able to measure in nanoscale, that is the accuracy, that accuracy is up to nano level. If you are able to measure in micron level, the accuracy is only in the micron level. That is how, you have to consider this. But still it is imperfect. Only God, suppose God creates two flowers. These two flowers are perfect. You cannot find any difference between these two flowers. Our two eyes or, anything. It's only God can create this kind of perfect, whereas human beings only produce imperfect components. This is what we hold in our hands, touch out in this shop floor. And it has the imperfection and variation allowed by the tolerances specified on the drawing. So today we are dealing about this. Imperfections. What type of imperfections we are allowing so that the function of the component is not affected. That is what we always say. This the manufacturing, inspection, assembly, and service personnel that maintains people always deal only with this. Day in and out, only deal with the imperfect, and nobody is having the perfect. Though it is made perfect geometry in the CAD model, it's not useful for us to use on our daily day in and day out functions. Now, there is one more thing, virtual geometry. For example, you take a center line of a hole. Drawing, we can happily give a center line, but in the component, are you able to see the center line? We'll see only a hole. It's not possible to see a center line, but in the drawing, very clearly with the dotted line, they will give a center line. So that is only virtual. That center line is only virtual center line. It cannot be seen or touched. Like that, any center line of a tab or any center line, any other things. So this center geometry, like axis of the hole or the center plane of a keyway or datums, we are dealing with datums. These all things are, imaginary. We cannot, have on the component. If somebody asks us, show the center line, we cannot show the center line. It's only we have to imagine that. And the part must be there. One more thing is this virtual, in order to create the virtual geometry, first of all, you have to manufacture the component. On the drawing, let us not take the virtual geometry. Part must be manufactured before virtual geometry can be derived. This is what I want to tell. These three types of geometries we are dealing in our shop floor. Okay. Now, let us see. This is a component. I will show the 3D. This is the 2D drawing. I will show the 3D drawing. This component, it is a block. It is having some thickness. and is having a length of 135 mm. It is having a width of 50 mm. And there are two holes in this. This is one hole and this one hole. Well, let us see how these holes are manufactured. The position of the hole is given from the bottom face 20 mm, and again from the bottom face it is 115. Whereas this side, this with this reference of this line, the position is given 30 m here. Whereas this 30 m is common for both. The center lines are falling in the same center line. Okay, let us see how they manufacture this. So this is the component. Okay, this is the component. Already manufactured component I have taken. What we do is a very, very vague. In the colleges we do. In the today's industry, all the things are only for explaining. I have taken this example. So this is a surface plate. This is our maybe scriber with a height gauge. Okay, so because the dimension is given here, this is a 0. This face we have taken as a reference. So we are resting this component on the surface plate, and the height gauge also, the scriber is also resting here. That means this level and this level are now 0, 0. Okay, so now we are taking this as a reference, and we are simulating this surface with the surface plate. Okay, we are simulating. Please note down that point. We are simulating this surface with the surface plate, and from the surface plate we are taking the measurements. So next what happens? Then what is the dimension it is given? About 30 mm it is given. So because from 0, we'll move the height gauge to 30 mm. And then after going to 30 mm, we'll draw a line like this. So we have made a line like this. Okay. So now we got the center point of these two holes. It is with respect to this, it is 30 mm. So this is the line. Now, these two, one line we already got, one coordinate we already got. The second coordinate now we have to get. So for the second coordinate, what he has done in the drawing, he has given with respect to this. First coordinate given, he has given with respect to this, not with respect to this or with respect to this. He has given not from this face, from this face. So we are resting this on the surface plate and simulating this surface on the surface plate. Now again the dimension is given here from this face. So we have to take this only as a reference, not this as a reference. So let us see how this is. Now we have again taken this surface plate and we are resting this on this, and we are simulating this surface and taking the measurement. Now again surface plate, this is 0. Now we have come up to this dimension and marking a line again. We have made a line again here. So now we have two lines for this. One is this y coordinate and this x coordinate. The intersection of these two is the center of this hole. Similarly, again we will move it up for this. And again we will make a line, and we got these two lines. Okay, now what you do, we will maybe make a center punch at the intersection and make a center drill. All the process, I am not going to details. This is how we are manufacturing a component. So now, this we have taken as a reference, and this we have taken as a reference. These two references, why you have taken? Because he has given the dimensions only from that line. So that means that is the datum of that particular component. So he has taken two datums. One datum is this and one datum is this. So now the datums are, very simple. I am just explaining. It's not that easy, but only to understand, I am just making you aware of what is datum. Now, what is the datum? Datum is a point. Even a center point can be a datum. On a drawing, see, if you make a 2D drawing, it's a line. Or if you take, plane, it is a plane, it is a surface or other geometrical surface from which dimensions are measured when so specified. This measured when so specified. See, here dimensions are, drawing is already given, component is manufactured. Then you have to measure the component. We have to find out where the datum is, from which face the drawing is, the dimensions are given. So that we have to take as a datum. So that is the datum. Or to which geometrical tolerance are referenced. I will just come to this geometrical tolerance. Now only I am talking about the coordinate tolerances. Here datum as an exact form. See here, when it comes, I will just explain the datum, whatever we are taking, What we do in the shop floor, we grind it because we are resting on the surface plate. That particular block, what we do, we'll do it a surface grinding operation of this tool. We say at right angle, maintain right angle in the shop. But why you are making right angle and grinding? Because it should have a perfect form. If there is a waviness or inclination, this inclination will again affect on the center distance of the holes. So in order to avoid and in order to have the perfect centers, what you do is we make some sort of grinding or fine machining or lapping or all sorts of things. So this is the exact form. We have to consider that is exact, otherwise there is no end. A datum has an exact form and represents an exact or fixed location. Okay, for the purpose of manufacture and measurement. It's only for the purpose of manufacture and measurement. Otherwise, it's not perfect. It's after all a human manufactured by a human being, which is imperfect. But still, we consider that as a perfect. Sorry. So now datum features. A feature, a center. Suppose we take now that reference we have taken the side face. That is a feature. That plane is a feature. That line is a feature. Drawing is consisting of various features. Edge is a feature. Surface is a feature. We call them as a feature. Center line is a feature. Okay. So datum feature is a feature of a part, such as an edge or a surface or a hole. Hole means, again, hole we cannot take. We'll take only central line of the hole, which forms the basis for a datum or used to establish the location of the datum. They're all, English. You don't worry about this. Understanding is more important. So how do you select the datums? That is very important. A datum feature is selected on the basis of its geometrical relationship to the tolerance feature and the requirements of the design. Let us just take this. See here, earlier last time we have discussed this slide. See, this is an assembly. This assembly, this one component is assembled here, and this center component is this. This is one. These are number is two numbers. One side coming here, one side coming here, and this is center plate, and we are fixing with some two pins, stepped pins. So here, what is happening? What the requirement is? There should not be any much clearance here, and there should not be any interference. When you assemble the components, the component this hole and this hole has to match. So that means this dimension. And from here to here, this dimension should be toleranced very carefully. Otherwise, there can be, interference fouling. This will not, when you put the pin will not enter if this is more. If this is less, what happens? There will be play. Okay, so this all depends on the requirement of the assembly. Here, what you do, we take this as a datum, give the dimension. This as a datum, give the dimension. Suppose you give the dimension from here to here, and again here to here, and again here to here. There is a parallel dimension, but the tolerance between these two, tolerance accumulation and stacking, at the last class we will discuss. So some tolerance buildup is there. That buildup will create a problem in the assembly. To avoid this, the datums are very carefully selected and identified on the drawing. Datum feature is selected on the basis of its geometrical relation to the tolerance feature and the requirements of the design. To ensure proper assembly, corresponding interfacing features of the mating parts should be selected as datum features. This is what I explained. Corresponding mating parts should be selected as datum features. Okay. However, a datum feature should be accessible. One more thing is, you cannot give a complicated datum where you cannot see or where people cannot measure that. When datum is taken, that has to be, we have to either take as a location or take as a reference. So if it is not accessible on the component, you cannot take that as an datum. Datum should be always accessible on the part and be of sufficient size. Suppose a small 1 mm size is given, you take as a datum and manufacture about 100 mm length of other feature. This will have a lot of variations. Magnified, the errors are magnified. So it should have sufficient size to permit its use. Datum features must be readily discernible on the part. And on the part, the datum, it should be readily discernible. That is why you use some symbols, I will explain. So we have considered. So application of datums. So now what happens is, datums are given, but where the datums are given, where datums are not given. Suppose you talk of a straightness, it is an independent dimension. No datum is required. Similarly, flat, There are not no straightness is an independent dimension. It is not depending on any other feature or any other relation. Similarly, flatness not have any datums. When you come to examples, I will explain to you. Then orientation and locational tolerance refer to datum. So, for example, you give an angle. Angle with reference to what? 30 degrees angle give. It will have a reference. Orientation and location tolerance refer to the related features. When you come to orientation, I will explain. So that what will have, the angle is given, angle with respect to some base phase. That will have a datum. And usually one datum is required for orientation purpose. Whereas when you come to positional relationship, for example, a hole, it needs minimum two, X and Y. Otherwise, you cannot find what is the position of that hole. It needs minimum two datum systems. These are designated, generally we use three datums, and these three datums are designated as primary, secondary, and tertiary datums. I will explain this. See, then one more thing is theoretical datums. Theoretical datums. See, earlier I used a surface plate. Surface plate is also manufactured by a human being, but it is accurate. But how much it is accurate? It is accurate to only some extent. It cannot be 0, 0. So they are also manufactured by a human being. Similarly, a machine table, a jig boring table, it's also manufactured. But jig boring table, when you keep the component, we always consider jig boring table is perfect. We don't consider any errors in jig boring table. We think that is a flat. Okay, and ring and plug. These are all, though these are manufactured by a human being, and there are some variations, already inbuilt variations are there, but we do not consider that variations. If you start considering all this, there is no end. We cannot manufacture the component, we cannot measure any component. So we have to ignore this and consider these, all the things are 0, 0. So the machine tables and surface plates, though the machine tables and surface plates, etc., are not true planes, but are of such quality that the planes derived from them. See, earlier I made a simulated datum, are used to simulate the datum from which the measurements are taken and dimensions verified. For example, ring gauge and mandrel. These are all called theoretical datums. Okay. Now, the datums are theoretical as datum features are created by manufacturing. Even the surfaces are not perfect geometrical surfaces, but they are intended to be of sufficiently high quality that any errors that may introduce are insignificant. Please note down, the errors introduced by the surface plate or jig boring or a 3D CMM machine or maybe any layer check, they are all insignificant compared to the component tolerance. Okay, this we have to remember. If there is no assumption, then we cannot go further. These are assumptions. Now, let us see. This is a pictorial explanation. These are component. Component, when you magnify this, the surface is like this. Though it looks now with our naked eye, when you magnify, these are the imperfections in this. So this we simulate. We consider for our purpose, we take this surface is like this. Okay. This is true geometric counterpart of the datum feature A. Okay, this is true geometric counterpart. And when you come to the surface plate, these also not perfect. This also will have some exaggerated. This also will have some variations, but these variations are, we take this as a simulated. This is this. Then we both put together. There may be some sort of error, but you ignore that error. But we have to consider this. This surface is almost resting on the surface plate. Unless we consider this, there is no end and we cannot go further. So like this. Now let us think this. Maybe these are all some theoretical, every one of you know this. See, when a component is kept in a phase, it will have generally 6 degrees of freedom. All of us know. Number of, because it can move in x-axis, it can move in y-axis, it also can move in the z-axis. They are all, translation movements, translation. It can move x and like this, front and back. And in the y, it can move like this. In the z, it can move like this. And it can also rotate about x. and about y and about z. This he is saying that here in the geometry is saying UVW. When you are dealing with CNC machines, they will call as ABC. See, the rotary axis in the x direction we call as A axis, and in the y axis called B axis, and Z we call C axis. Okay, all are similar. Here he is calling it UVW. If you go to know what you call the wire cut machine, we will have XYZ, ABC, and also their UV axis are there. They are all parallel axis there. So different nomenclature, but the meaning is they are having two moments in this, two moments in this, two moments in this, and rotary axis, rotary axis. So all put together is 6 degrees of freedom. Some people say 12 degrees of freedom. They say plus and minus also. Let us not bother about this. There are degrees of freedom. One is in this, one is in this. This is the translation movement and the rotary movement. These are what. So these 6 degrees of freedom are to be arrested in order to immobilize the component. So now, if you take a component, let us see how the component. This is x-axis. So in the x-axis, it can move like this. It can also rotate around the x-axis. This is called roll. Rolling, you would have heard rolling, pitching, and yawing. Roll, pitch, in the theory missions, all of you study in, maybe in gyroscopes and ship, gyroscope, couple of ship and boat, when consider, no, we come across this words roll, pitch, and yaw. This is called rolling, and this is called pitching, this is called yawing. These are all rotary axis. So this can move like this, and also it can rotate about this. And this can move like this, this also can rotate, and this can move. So these are the 3 degrees, and this is of axis. So now we have to arrest these 3 degrees of freedom. See, what you do when you take a component, you keep on a surface plate. This or surface plate or a jig plate, when you make a jig, what you call that, drill jig, you have to rest on the jig plate. So this is what you call as a primary datum. So what is primary datum doing? See, this primary datum is not allowing to move in the z direction. It is not allowed to move. And also this rotation of, pitch, that is roll and pitch are controlled, is not allowing to move. Only moment where it is there is, it can move in this direction, it can move in this direction. But z-axis movement is arrested, and these 3 rotary axis are arrested. This is 3. Okay. I'm coming to 3-to-1 principle. See, in colleges and our tool design, we call 3-to-1 principle. I'm explaining what is this 3-to-1 principle. Okay. So what people say is, when you keep this, there are minimum 3 points it will touch. It can touch more than this, but minimum 3 points it will touch. Once it is touching on minimum 3 points, the surface is stable. Okay. Next. This is now what you do. We have arrested this. We have kept on the primary datum and arrested 3 degrees of freedom. Now what we are doing, this secondary, we are keeping one more plate here, perpendicular to this primary datum and resting against this. This is secondary datum. What is it doing? This secondary datum now what is doing? It is not allowing the movement like this. Okay. It will touch at 2 points. But there is a slide movement here that is still there. So it is not allowing like this, and also not allowing to move in this direction. But there is a sliding movement, one more is there. So first primary datum, what is doing? Primary datum is arresting 3 degrees of freedom. When you go to the secondary, this is arresting 2 degrees of freedom. And next what we do, again keep, to arrest this movement, we keep one more plate here. This is the tertiary datum, the third datum, tertiary datum. So this will generally touch at only 1 point. This is mathematically proved and this is well agreed. So this is arresting. Now the total component is totally movements are arrested. So now this is arresting. This is arresting 3 degrees of freedom. This is arresting 2 degrees of freedom. This is arresting 1 degree of freedom. So 3 to 1 principle. This is called 3 to 1 principle. Our Rangareddy sir will be well knowing because he's a tool designer from CITD. This is what they teach now when you locate a component in jig plate or milling fixture. Okay, these all the three are to be arrested with this. That is how now we have to select the datums. Now, when you see pictorially, the component, these are all imaginary. They are not there. We have to imagine these all the things. We have to imagine a primary datum. We have to imagine a secondary datum, tertiary datum. And the component, because this component is kept touching this and this, it is immobilized. The component is now immobilized. It is not, the movements are not allowed. And this axis is called datum axis. The intersection of this secondary and primary is called the datum axis. Similarly, the tertiary datum and this intersection of this is also called datum axis. These are three datum axes. One is this, these three datum. Please imagine, that's only imaginary. Okay, I will go to next one. Somebody say, Ajit raised his hand, and can we reserve our questions to the end of the session? Because once you start question answers, no, what happens? We'll be stuck up there, and our time, limited time will be spent. We will have question answers on fourth day, fourth session, full day, almost more than 1 hour. We'll have question answers. Or if you still have any questions, you please send me my mail. I will reply by mail. I have already given my mail address and phone number. Okay. Please excuse me. Otherwise, if time permits, I will answer your questions. Because this is a 5-day program, actually. If it is conducted in ISKI, they conduct for 5 days, full 5 days. But I have to complete this within 8 hours. Already 2 hours lost and 1 more hour is lost. Left for me is only 5 hours. Out of 5 hours, 1 hour I am taking for question answers. So within 4 hours, I have to complete this entire GD&T tolerances. So please excuse me. So now this is the datum reference frame. There are 3 mutual frame. So the frame exists in theory only, but we have to only imagine this. Now, this simulation, the internet is not stable. Now, this simulation is accomplished. This simulation is accomplished by positioning specifically identified features in contact with an appropriate datum simulators. See, datum simulator is maybe, drill jig locating pins or a base plate, or here when you take a measurement surface plate, or if you go to 3D CM, you need not worry. It will decide the datums. The moment you say the datum, it will dial on the surface and take the 3 points and take it as a primary datum. Dial on the entire surface and take a secondary datum. The CMM, everything is inbuilt. But today I'm not touching the CMM. I am only talking of the today and tomorrow next class. I am only with conventional equipment. There is no CMM. Olden days, there is no CMM. But still people are measuring the components. So how to measure without the CMM? The basic knowledge is required. No, if you use CMM, nothing is required. It will do everything. But my class is only to give some sort of inputs, how the components are measured and how the design is to be made for measuring this. So now identification of the datums. This is the datum symbol. This is ASME. They have given very clearly. Every proportion is given. This is the datum symbol. This is 1.2. There we give as ABC as a letter height. It should be 1.2 times of the letter height. Everything is there given, and it should be 90 degrees apex angle. Because you should not get confused with the arrow line. That is why they are given all this. See, when you make a dimension and give an arrow, the arrow should not get confused with the datum line. That is why they are given it a different specifications. This is now how they so accurately they made this ASME Y14.5. That is why there is no controversy. There is no, people are not going to court or not having any disputes, no arbitration, because everything is very clear. And this is how, on a component, we show the datum. Suppose this diameter, we are taking as a datum. And with reference to this, probably we are making this or making some holes. And this how we show a datum. This datum symbol is just placed on this dimension line, and there is a box. In the box, the datum. The datum A is, that is inserted. And so if a single datum, this kind, when you go to the geometric dimensioning and tolerance, we will find this kind of boxes only. This is a single datum. This single datum here, there are three boxes are there. First box will give the geometrical tolerance, maybe straightness or flatness, or maybe perpendicularity or angularity or position tolerance. This all will come here. The second one is the amount of tolerance. What is the amount of tolerance allowed? See, please keep in mind, my young boys, this is nothing to do with the size tolerance. Size is different, form is different. I am only talking of the form tolerances, not size tolerance. Size tolerance means you have to go to IS 696, where H7, 10H7, H7, A7, B7, alphanumeric letters. That when you come to this, first you have to ensure that the component is meeting all the requirements of the size tolerance. Then only you have to come to this geometry. Okay, geometrical tolerances are not going to measure the size tolerances. So this symbol, whatever it is given here, is only geometrical tolerance. And this is the datum reference. A. A means there is a primary datum. Here you see, here given three datums. Always this is in order. This is always in an order. A is the primary, B is in secondary, and third one is the tertiary datum. You write CBA. C is always here. Whatever is coming in the first box is always a primary datum. Please remember that. You may write, maybe A here and C here, but still this C is primary datum. We have nothing to do with the sequence of the letters. We are only worried about the boxes, first box, second box, and third box. Okay. This is how, datums are specified on the drawing. Now, let us see this component. This component is having a position tolerance. When I come to position tolerance, the symbols and other things I will explain to you. This component is having a 3 holes, and the dimension between this hole to this hole is 75. This is a box dimension, true dimension. And from here to here is 150, and again 75. This is the datum A. The bottom surface of this component is datum A. That is the primary datum. And this is datum B. The side surface is datum B. And he has also given C datum. Let us find out where is the datum C. A, B. Here, this is inclined surface is datum C, the tertiary datum. So he wants these holes to be made with respect to this one, and this one. That means the whole axis and any of the inclination or position of these 3 holes should be in relation with the datum A, datum B. That means when you take with relation to this, it should be perpendicular to this. This whole axis should be perpendicular within point 1. Okay. When you take this, the whole axis is to be parallel with respect to this. When you take this, the plane passing through this should be having at an angle of 45 degrees. So, but all put together, the total tolerance is 0.1. So, how do you generate this 3 now in the datum reference frame? Now, the datum reference frame is like this. This is your primary datum. This is the bottom plate. Though in the drawing it is showing like this. This is the primary datum. And this is our secondary datum. That is the B. Component is resting on this. So, this is the plane it is resting on. This is the primary datum, first datum plane. And this is the here, so we are keeping something here, maybe some pins or some plate, we take it as second datum. And this datum, whichever is perpendicular, now it is inclined with a 45 degrees basic angle and resting here. This is the tertiary datum. This how we have to take this. With all the 3 datums, we have to take the measurement of these 3. When I come to this measurement, we will, this only just, to explain about the datums. Next. Now, whatever I had shown earlier is only surfaces. Surfaces will not have size. Lines will not have any size. Points will not have any size. So, points put together will form a line. And some lines put together will form a surface. But these 3 will not have any sizes. But when it comes to, solids like diameters or plate thicknesses or all these things, they will have size. So the datum features such as diameters, widths from singular flat surface, that they are subjected to variation in size and form. Here you see, one more new thing has brought. Earlier, whatever I have been telling is only form variations. Now, size is also now is bringing it. Variations in size is also coming. So, because the variations in size are allowed by the size tolerance, it is necessary now to determine whether they are at RFS, MMC, or LMS. Earlier is explained, last class, our friend has explained about what is MMC and what is LMC. Again, I will explain. MMC means maximum material condition of that feature. LMC means least material condition of this feature. RFS means regardless of feature size. Here, it is neither LMC nor RMC. It is any size in between the tolerance. That is regardless of feature size. Okay. RFS is generally denoted in the world and standards as S, MMC with M, LMC with L. But now RFS, if you do not mention anything, it is generally considered as RFS. So now we are going to slightly further. Not only with the form tolerances, we are also now dealing with the size tolerances. Okay. Oh, time is very short. So now, before this, you take this as a drawing. This is datum A, this is datum B. Okay, this is a component, and this in this component, these are 4 holes. These 4 holes are given with respect to this datum A and datum B. And here is not given, only to make you understand how the datum, if they are interchanged, what is the problem we face. So now, because he has not given these two, we will take this. Now what he has done in this drawing, datum A and B, he has given in this sequence. Suppose this 0.2 dimension, the position of these 4 holes is within a cylindrical tolerance zone of 0.2 when it is at the maximum material condition with respect to datum A and datum B. So because he is taking datum A as a primary, we always locate this first. So once you locate this datum A, any type of inclination in the datum B is no, it will not really touch, it will not touch at 2 points because datum A at 3 points. This is a true geometric counterpart of that, datum feature A. Whereas datum feature B is true geometric counterpart but perpendicular to datum A. But this will not touch. So this is when you say of A and B. Suppose, let us talk of B and A. Now what he is doing, it's only to say that order is very important in the datum. When you mention the datums ABC, order is very, very important. So if you do not take this as a primary and secondary, if you take this as a primary and secondary, is not accepted. Primary, secondary, and tertiary datums. This is how Maybe letters may be B or A, B or anything you write. Here what he has done, he has taken B and A. When you take B and A, now this has become the primary datum. So now we are resting the component on this. And this has become the secondary datum. A has become the secondary datum. Now you see what is the true geometric counterpart. So this component will be like this when the datum is changed. When you come to this maximum material condition, again the tolerance is also now this is the virtual condition of this datum B, datum A. So virtual condition again it will increase because the geometric tolerance also will increase, will go. Here what is happening? It is within 0.2. This is 3.1 to 3.2. Within this 0.1 tolerance, it can be inclined. When you take geometric, it is again 0.3. This tolerance plus this tolerance, it will become 0.3 of the virtual condition. So this is very, very important, specifying the sequence of the datums. Okay. Now I will go to next one. So this is how specify on the drawing. Suppose we specify this is the plane is same. Because the plane is same, we have specified A and B, and here the datum is A dash B. And the common plane, datum feature A and datum B, datum plane A and B is a common one. If if anybody wants me to go slow or fast, I can go because time is running very fast. Rangareddy, you have to give that. If you want me to go fast, then I will go fast.
No, sir. This speed is okay, sir.
Okay, sir. Okay. So now there are two multiple datum features. There are two diameters on this, and with respect to this multiple datums, we have to maintain this surface. Here again, it is given as a multiple datum features. Okay. Now this is specified like this. Now there is one more. See this component. Let us see. This component This symbol I have not explained. When you, in the dimension line, when you put a circle like this means this all over. This is not there in IS 696. This is there only in ASME Y14.5M. Please note this, my younger young friends, please note this. This symbol here, a circle is given. Okay, this circle means this profile tolerance is all around this component. Now let us understand the drawing. Here, this is a component, this is the datum A, and the dimension is 75. 4x R12, that means 4 numbers of R12 are there. 1, 2, 3, 4. We earlier used to write as typical. Now no more typical. 4 times 4x R12. 4, these radius are R12s are available on R12. And 8 times R10 here. 1, 2, 3, 4, 5, 6, 7, 8. And this 4 numbers of holes. This hole size is 12.3 to 12.4. And the holes are referenced with a position tolerance. This should be with the position tolerance with datum A and B. When the B is at the maximum metal condition again. Here, this is the B. These 2 holes he has taken as the datum B. These 2 holes he has taken as the datum B. Okay. So now with respect to these holes are to be, that means they should be parallel. These both the axes are, it should not be offset. This axis should not be offset more than this tolerance. Suppose this center can be somewhere here, this center can be somewhere, they can be offset. Or this can be inclined like this, or this can be inclined like this. All the inclination and offset of these 2 holes, that is why he is giving datum B. And with respect to datum A, this is surface, and these are to be perpendicular with respect to the surface. When I come to position tolerance, I will explain all this. So the drawing calls for a profile tolerance of 1 mm with respect to datum A and B. So this profile tolerance, actually component is this profile tolerance 0.5 this side, 0.5 this side. And this is how we give the datums. When it comes to actual topic, these are all examples. I will explain there. So now datums are over. So what happens now? Suppose there is a casting or there is a weldment. See, when you take earlier, I was telling when the datum plane, when you take, you have to grind it, you have to machine it very perfectly. Suppose you take a weldment or a casting, we cannot machine it because it's a big casting and a lot of expenses are involved when you machine it, or a weldment, or a big frame, very big frame. These all the things, then there, what you do is, we will not totally take the entire surface as a datum. There we take some points, specific points, based on buttons. Generally, when you look at thing, when you make you will not, the primary datum is not totally resting on the base plate. We will give some buttons, 3 buttons. It will be resting at the 3 buttons. These 3 buttons are resting, that is, the entire surface is not resting on this because the irregularities are already there in the surface. That irregularities are transferred to the when you do the machining of other features. So in order to avoid the irregularities, we take datum targets. We take 3 pins or 2 pins or 1 pin. They are all called datum targets. They are generally used in weldments, castings, forgings, and thin sections. You just remember there is one more word called datum. Datums is a entire surface. Datum target is only points. They are generally specified like this. So this is weldment. We make a locating pin. Here like these 3 pins. If it is primary datum, we'll give 3 pins. Secondary datum will give 2 pins, and tertiary datum will give 1 pin. Then 3 to 1 again. These are all called datum targets. It is only to avoid the entire surface touching on the plane and avoid machining, further machining, and making it very, very accurate phase. Okay. Now this is the datum target. This is how it is specified. Dia 12. That means the pin diameter is 12, and the P1 is the datum target number 1. That is the primary datum target number 1. And you make a pin of diameter 12 and let it rest here, the entire surface, and that dimensions are given again. Because here he has probably you would have made some spot facing, or you would have some grinding, or in the casting probably he is getting a perfect point there. That point is selecting and that is taking as a datum. These are all datum targets. Now, we'll go to actual geometrical. Till now, geometrical tolerance you are not gone. Now we'll go to geometrical tolerance. See, last time we have discussed why geometrical tolerancing is required. So this is one component, and this is one component. These two components have to be assembled. So when you when you manufacture this component, this 49.6, this 49.5, and this face is just inclined like this. We have to accept the component, because when you make the size, the 49.5 is well within the size, the 20.2 is well within the size, and the center is 50.1. It is actually 50 plus or minus 0.2. So within 0.4 tolerance, it can be inclined. The axis can be inclined within 0.4. So when you assemble this component, it is not assembling. This we have discussed last session. I am just repeating. So, but when you assemble, this is falling here. Okay, this is the danger of when you assemble the components. So in order to avoid this, we are given a perpendicularity. Once you give the perpendicularity, it should be within 0.2. So this axis is to be perpendicular with respect to this datum A within 0.2. Now, because 0.2, y is given, there is clearance more than 0.2. So because there is a clearance more than 0.2, it will automatically assemble. Even though there is an error of 0.2 perpendicularity tolerance, it will assemble. So this is how we give the geometrical tolerance. This is the purpose of the geometrical tolerance. Otherwise, assembly is sometime our president was telling R&D is done at America and design is done in India, and components are manufactured in China. All these things have to be coordinated. That's how Narendra Singh Saab said in the first inaugural session. Different locations, they are all made, and all the things, once you purchase a loose component or once you purchase a spare for an automobile, it has to just fit in. Otherwise, you have to call back from the entire world, all the components and replace. This is the danger of this. That is how the geometrical tolerances are useful. Now, definition. A geometrical tolerance is the maximum permissible variation of form, orientation, or location of a feature from that indicated or specified on the drawing. So the feature would be permitted to have any variation of form or take up any position within a specified geometrical tolerance zone. That is the definition of this. See now, form of a line. It will have straightness, roundness, and profile. This line. When you come to a surface, it will have an error of flatness. We generally call flatness, cylindricity, and profile. Now, orientation. Orientation is angularity, parallelism, and perpendicularity. When you come to location, position, constancy and symmetry are location tolerances. And runout, these are special composite tolerance that we'll discuss when you come to maybe the fourth session, we'll discuss on this. So now the geometrical tolerance is generally specified like this, already explained. This is the straightness symbol, and within this 0.15, the straightness is to be contained of the component. And the symbol and the tolerance value, the frame height. This frame height also earlier I explained how much is the frame height to be given. So now let us see. Suppose we want a straightness. Line elements. Though it looks a surface, it's only line element surface. Line element means only line elements you have to measure. Here the line elements are, that means we have to move one direction straight. It should not crisscross. If it is crossing side, then it's a surface. So it should be moved straight like this, and the variation of the straightness should be within 0.15. This is on the outline of we can make like this. Then once you give this kind of symbol, the tolerance refers to the line or surface itself. Next, here one more. This is only confined to this step. On an extension, when it is confined, what you have to do will not give on the size. This is the extension of the surface, we'll give here. That means this is referring to this. And the third one we are giving exactly on the dimension. So this is referring to this center line. Okay. So depending on the termination of this arrow, the meaning changes. Should be very, very careful. And this is one more. Here, either you can given a center line. This center line means it applies for both this diameter and this diameter. So there are two features. One is this diameter, this diameter. The once you give on this applies to both the diameters. Okay, this is how you know this is given. There is one, sometimes now we'll give composite tolerance also. He wants, this is a round component, and he gives one is straightness, other is roundness. These two, the straightness required is 0.12, roundness required is 0.04. These two things he is giving in a drawing. That means when you take the end view, the roundness is within 0.03 and the straightness is 0.05. Okay, this is the meaning of this. And see here he has given on the center line, but if you do not mention anything, it is applicable for this diameter and this diameter. Suppose you want only for this conical portion, you write as a cone, because you cannot give a tolerance on a geometrical tolerance on a conical point. We will be giving on the center line. Then you write as a conical portion only. Suppose you want to only on diameter 8. The position tolerancing. See, this is, I have taken 3 examples. I have taken 3 examples. Let us take this component, it's a coordinate dimension. There is one hole, and the dimensions are given 20 plus or minus 0.1 and 16 plus or minus some tolerance. This is one type of dimension. This is called coordinate dimensioning. And next one is the 16 and 20 are kept in boxes. And there is one symbol given as with a circle with 2 lines, that is a position tolerance, with a spherical tolerance of 0.2, but the same hole is 15 plus or minus 0.8. Here also 15 plus or minus 0.8, but the hole position tolerance is mentioned. And these 2 are kept in box dimensions. And when you come to this, here same dimension, but here what happened, the 16 box he has kept 20 in the box, and here he has added one more symbol is M. That is the position tolerancing at MMC. Let us see what is the meaning of this. See, this is the first one drawing is like this. So the center of this 16, it can be 16.1 or 15.9. So 15.9 to 0.2, the center can vary from here to here. Okay. Now, when you come to 20, this is 0.2 tolerance, and the minimum is 19.9, and the max is 20.1. So this is the 0.2. This is a square tolerance zone. This center of this hole can lie anywhere in between the square. It is allowed because the tolerance are here plus or minus 0.1. Here the tolerance are plus or minus 1. The tolerance zone for the center is given as a square of 0.2 side. Then let us come to this. This is here what he has done is, here the tolerance is changed is 16 plus or minus 0.1, here 20 plus or minus 0.2. So then what happened? This is a rectangular, it's not a square, it is a rectangular tolerance zone. Because here the tolerance is increasing. So here 0.4 is the tolerance. Here 19.8 to 20.2. So this is 0.4 tolerance zone, whereas this is only 0.2. So now, whereas the tolerance are equal for both the coordinates, we are getting a square tolerance. When coordinates tolerance is changed, we are getting a rectangular tolerance zone. Let us come to polar coordinates. Here, the polar coordinates are given as R32 and angle 30. Okay, so when this R32, it can be 31.9 or 32.1, the radius of this. Similarly, the angle can be 30.5 or 29.5. So now the tolerance zone is like this. See, this is the tolerance zone. This is now almost, these are radius, in between these 2 radii and in between this angle, this is the tolerance zone. Are you able to make, are you able to see this stuff? Sir, is it clear?
Sir, clear, sir.
I can go.
Yes, sir, clear, sir.
Okay. So now this, let us see this. This is the sphere tolerance, the rectangular tolerance. This is a polar coordinate tolerance zone. So now one simple example we take. This is the component. This component 1 inch is the x coordinate for this hole, and the tolerance on this is 0.007 inches. See, when you say inches, no, 0 need not be added. When it is mm, no, 0.007 we add. In the olden days, when it is inches, no, they never used to only 0.007. That is inches. So now let us take the position of this. The position of this hole is 1 mm in this direction and 1 inch from this direction and 0.7 inch from this direction. The tolerance on this is 0.007 plus or minus 0.007 inches, and in this direction is plus or minus 0.004 inches. Now, if you take this, now this is not equal. Otherwise, it would have become a sphere tolerance. Because the tolerances are not equal, the tolerance zone is a rectangular tolerance zone. Okay. Now, the rectangular tolerance zone, there are 4 points. These 4 points are the extreme points. These extreme points, we are allowing the tolerance to lie within the extreme points. When we are allowing this tolerance to lie in the extreme points, it is observed and accepted that if you calculate this diameter and make entire this rectangle into a circular zone, there is no effect in the clearance and functional aspect. So now what we are doing, we are calculating the diagonal of this. The diagonal, how do you calculate? This square plus this square root of addition of these two, square root of this is 0.008. That is this diagonal. And double this, we will get the radius, that is 0.16. So now what we are doing, let us be here, just try to understand. This rectangular tolerance zone, we are taking the 4 corner points. These 4 corner points is, the diagonal is 0.016, and these 4 corner points now we are converting into a circular tolerance zone. And now the tolerance zone is circular. Okay, this 1 mm, the tolerance zone is circular. What we have done, the tolerance from here, we have eliminated, we shifted here. Okay, the tolerance from here and here is, we are not mentioning here. We have shifted the tolerance to here. Okay, but we made it as a circular zone. Now, next, let's go to next one. So now let us see this. What we have done, the same component, we have taken 1 mm, but we have put this in a box. And the same 0.7 inches, we have again put this in box. And here we have added a symbol. And here we added some value, that is 0.016. That means the tolerance on this and the tolerance on this is shifted to here. Now the hole can vary within a diameter of 0.016. When the hole is at maximum, that maximum metal condition will come when it comes to maximum metal condition. Now only position tolerance, please remember this position tolerance. Okay, is it clear? Now if it is clear, I will go to, this is the basic difference between our coordinate tolerancing and position tolerancing. Is it clear, sir? Rangaraj sir, if you say yes, I will go further because I will take only.
Please go ahead,
okay.
Sir. Yes, sir.
So position tolerance, now we have avoided the coordinate tolerance and the coordinates are kept in boxes, and now these are called true dimensions. True dimensions. I will explain why they are called true dimensions. When you go to gauge design, I will explain. This is a true dimension, and whenever you keep this kind of dimension in a box, this is called true dimensions. They are the basic dimensions. Some people write as basic, some people write as true dimensions. And the tolerance is now given for the center of this hole. Position of the center of the hole is given here, and the tolerance is mentioned here. Okay. Next, how do we mention this on the drawing? So now there are 8 holes on this drawing. These 8 holes, the hole size is 4 to 4.1. and it is having a position tolerance of 0.25. The whole center can vary within a position tolerance of 0.25. It can vary within a 0.25 circle diameter, all the 8. And the PCD of all the holes is 26.12. That is also in box dimension now. Okay, so now the angle is kept in box dimension. The PCD is again kept in box dimension. So now the tolerance is shifted here. This is how specify on the drawing. Now this is the position tolerance, how we specify on the drawing. Okay. Now this is the symbol of the position tolerance. Please do not get confused with the circularity tolerance. Circularity tolerance will not have these two lines. The cross lines will not be there. With a circle and cross lines is a position tolerance, and a circle without these two lines is a position is a cylinder circularity. Okay. This is the dimensions. Everything is now given the standard, and they have fixed everything. Nothing is left to chance. And what is the frame height, and what is the how much is that symbol we have to give? All these things are given there. Now, one example. 20 minutes time is there. 20 minutes is there. Probably we'll try to complete within 20 minutes. Today's. You see, let us take a component. This component is regardless of feature size. That means the feature size here, the diameter xxx is not neither it is a LMC basis nor a MMC basis. It is not a least material condition nor a maximum material condition. Anything it can be there between the tolerances, whatever is given on this. It can vary. So once you take this, the position tolerance symbol is 0.24 on the diameter. The position tolerance symbol is given here. Either you can give it here or here. Only to make R is written here. You can give here or on the center line also. That is the meaning of this. Only to make us know both are correct. So now the position tolerance is 0.24 diameter. And the basic dimension is 19. The basic dimension is 19. You see that there is no variation allowed. The basic dimension is 19. But once you take this basic dimension as 19 and basic dimension as 16, you find the theoretical center and allow the center to vary within the tolerance zone of 0.24. Theoretically, it should be here. But you are allowing because of the position tolerance. So now, once that is made, how do we measure it? The measuring is a very, very difficult thing here because there the tolerance, for example, the tolerance is plus 0.5. It can be, you take even 1 micron, 5 micron, 24 plus 0.5. It can be 24.05, it can be 24.1, it can be 24.5, anything in between the tolerances because it is regardless of feature size. In such a circumstances, measurement is very, very difficult. So in such cases, what you have to do is, first you have to take the measurement of this hole. What is the hole size? You have to take and the size, any instrument, you have to measure the hole size. For example, it's 24.1. Because the tolerance is 24 to 24.5. 24 within 0.5 can. Now, when you manufacture the component, it is measured at 24.1. Now you take the 24.1 and make a plug, a mandrel. So that mandrel, maybe if it's a 24.1, you make a mandrel to G6 tolerance or G5 tolerance, and it is to be slightly fitted. It's with just tapping, it has to go inside. Suppose, so how many mandrels are required? Umpteen number of mandrels are required. If you do not go for the MMC size or LMC size, because it can vary anywhere, 24 to 24.5, then 1 micron, 2 microns, even measurable, depending on the instrument what you are measuring. So that many number of mandrels have to be made. If you have to take that as a reference. Now, after making the mandrels, you have made this snug fit into this, and this is a rotary table. On this rotary table, it is revolving around a theoretical center of this. On this rotary table, because the component dimension, what he has given, see here he has given this, theoretically it should be 16 here. Theoretically it should be 19. Okay, so what we do, we go to a jig boring machine or any accurate machine, and with respect to this is a gauge. Here. and put a pin here. That is the pin is put here. We are not talking of the component, we are talking of the fixer for measurement. Here, one hole we are making, and other references here, that is 16 and 19, I think. It is 16 and 19. So one side 16, other side 19, we will go to 16 and 19. And with jig boring machine, with respect to this symbol, we will go to 16 and 19 and make 2 pins. Now, theoretically, this and pins are almost 0, 0. It is basic dimension. So you have the basic dimension tolerance on the fixture. So you are simulating that. You are simulating that. Now what you have done, you have put a snug fit mandrel in this and inserted and let the component now. It will not rest on this. Let the component touch these two things, and here a spring loaded support to keep, and from here you with a some sort of apply pressure here. Then it will touch here and here. Okay. Then rotate this and take measurements at a distance of a. That is this A is the thickness, make measurements from here and here. And the difference is the, then, because it can be inclined like this, then you have to correct for the inclination, take measurements like, it is a very, very, laborious process to find out the two measurement. If the size tolerance is not given, that modifiers are not mentioned, MMC or LMC. So this kind of difficulty to avoid, we are going for MMC or LMC. And then, then let us see this. Now, suppose that fixture is not there. We take a vernier and measure. This we can measure with a vernier or any other measurement, and we can take vernier. Now, there are 4 components. I got this kind of tolerances. It is the component size is 16. This is the position tolerance is 0.24. When this is made 16.12 and 19.05, generally we consider that is well within this. Well within this. We will say that the component is accepted, but the component is rejected here. General conventional shop floor, if you take the measurements with our vernier from here to here measure and take the half of this hole, then we will get this size. And from here to here you measure and take the half of this hole, and we will get this. The 19 is now measuring as 19.0 and 16 is measuring 16.12. We think that 0.12 is within this 0.24, but this is rejected. Okay, because we have to take the diagonal tolerance. Now we should not take this straight tolerance. We have to take what you have to do 0.12 square plus 0.05 square, add these two, and then you square root of this. If that is within 0.24, you can accept. So this much cumbersome, calculations and cumbersome equipment is required if you do not add MMC or LMC. So to simplify this measurement, the MMC and LMC are added. That is I just want to say the importance of MMC, LMC. That is how I taken this. So the components are rejected now. Let us go to next. Now what you have done? We have put a symbol MMC. Now we can use a gauge. So gauge pin is always made at a MMC plus geometric minus geometric virtual condition they call it. When it comes to virtual condition, I will explain. We will find out the virtual condition of this hole and make the gauge pin. So what kind of variations it can be there? The hole can be at the least material condition, or it can be at the maximum material condition. If